So we can move on, right?
Yes, Dario, we can move on. We have your screen ready.
So the first speaker for this part of the session is Rafael Barros from USP São Paulo. And he's going to talk about hybrid quantum frequency conversion. So, Rafael, please.
Thank you very much. Do you all hear me well on both sides? Yes, okay. Yeah, it should be.
Very good. Yeah, we can hear you.
Okay, so first of all, thank you very much. It's a pleasure to be here. And today I'm going to present work that I developed before I got my position here in São Paulo, when I back at Tampere University, where I did a postdoc there. And the work is called hybrid quantum frequency conversion, and it quite literally shines light into a slightly different problem, but it's still connected with what Simon and Yiwen just mentioned, which is the quantum frequency conversion, or, quantum frequency conversion, or QFC for short, is kind of an optical version of the quantum transduction, which maybe more of you are acquainted to. So in the optical domain, the quantum frequency conversion happens when you have an input signal of a few photon signal that interacts in a nonlinear crystal, in a second order nonlinear crystal typically, with a very strong classical coherent field, which here we call the dry field. So if you have an input photons with, let me try this out. If you have input photons here with a frequency omega-1 and the dry field with a frequency omega-2, then in the sum frequency generation process, you generate, you convert the photons to a frequency omega-3, which equals the sum of the two frequencies. And the dynamics, the quantum dynamics of this process is very well described by a beam splitter interaction that is represented here by this Hamiltonian, where this constant kappa here is tuned by the intensity of the dry field. And of course, the quantum frequency conversion, as the frequency transduction, finds uses in many different quantum technologies, especially in the detection of single photons, where it's difficult to measure directly, for example, and also in the interfacing with other physical systems, or in doing, for example, the Hongo-Mandel interference between photons of different colors, and a plethora of very interesting experiments. But today I'm going to talk about a slightly different problem, or let's say a different question, which is what happens when you perform such a phenomenon, the quantum frequency conversion, using a dry field that is not trivial. For example, here I'm considering specifically a dry field that looks like this, which is a non-separable field of two different degrees of freedom. In this case, the degrees of freedom are the polarization and the spatial profile. So just so we all understand it before I go forward, here I mean that, for example, my dry field is a superposition of a Hermite Gaussian mode, which has two lobes with opposite phases with a horizontal polarization, Hermite Gaussian horizontally oriented and horizontal polarization, with a rotated version of this. So a vertical polarization with a vertically oriented Hermite Gaussian mode. And because these two polarizations are orthogonal to each other, and so are the spatial modes, you cannot say that this field is polarized. So if I ask you what is the polarization of this field, and you measure with your apparatus the Stokes parameters, you're going to have to tell me that this field is completely unpolarized. You have sunlight. And that's because there is some correlation between the degrees of freedom, which if you trace over one, you end up with a mixture or the equivalent of that in the other. And in the interaction, in the quantum frequency conversion interaction, it's interesting because the nonlinear crystal has some frequency selectivity to it. So for example, imagine that I interact this dry field with a linearly polarized field in a crystal that only works for the frequency conversion when the two input polarizations, they are orthogonal to each other. So this frequency selectivity will fix, for example, that if your input polarization is horizontal, then only the vertical spatial mode of the dry field will actually contribute to the frequency conversion. So you end up in the end with a vertically oriented spatial mode in the frequency conversion. But of course, if you change the polarization, the figure that is upconverted rotates accordingly. So you're transferring, in a sense, the information from the polarization degree of freedom of the input to the spatial degree of freedom of the output, with the with the detail here that you're doing it with a different, from one color to another. So the question we want to answer here is more like, okay, we know that this effect can happen in the classical domain. It's just some frequency generation with some details, but what about the quantum domain? Can these correlations between different degrees of freedom be transferred somehow to the quantum regime? And we investigate this question quite deeply, both theoretically and experimentally. I will try to go a little bit through each part. So theoretically, we describe the frequency conversion with a Hamiltonian like the one I just mentioned before, which is shown here. But the dry field in our case is given by a superposition like this one. So it comprises a superposition, a general dry field, so a superposition of all combinations of polarizations and spatial modes. So polarizations either horizontal or vertical, and spatial modes either horizontal or vertical. So this field can be equivalently represented by what is called a coherency matrix, which is a classical analog of the density operator, for example, which allows you to quantify all the degrees, all the metrics of the correlations between the two degrees of freedom, just like we would do in the quantum domain. And with a dry field like this, the interactions that can exist in the crystal are those that are shown here. So basically, this figure is showing what amplitudes of the dry field contribute to which process. And if you want to describe then the final state, upconverted state in terms of this dynamics, you have to do a few steps. So first we start with a density operator rho of omega 1. We evolve it in a closed quantum dynamics with the Hamiltonian H to a two-color state that is rho of t. So after you perform the upconversion, there is a probability that this photon is in one color, but it can also be in a different color. So in the end, you have a macroscopic superposition of a photon in two different colors and two different degrees of freedom. But that's not what we are interested in. So we want to look specifically into the upconverted field. So let's post-select onto the case where the input field was upconverted. So if I have a single photon, I'm going to look into the case where this photon was upconverted to the different color. And in this case, you have to project onto the subspace of the upconverted color. And you can summarize this dynamics in an interesting way. So you can summarize it as in the form of a superoperator, which has a channel state, in the channel state duality representation here, we can represent it using a Choi matrix, or a Choi state, as we call it, which has all the information that the quantum state has. So basically, this channel, the superoperator E, can be represented by this state rho E. And what is interesting, and it's maybe the main theoretical result that we have, is that, in fact, this Choi matrix is the coherency matrix of the dry field. So this example of quantum frequency conversion driven by a non-trivial light field shows one rare case that you have a mathematical structure that exists in both classical and quantum regimes. And here, in this case, this non-separability between the degrees of freedom is manifested as a property of the channel. So all resources contained in the correlations between the different degrees of freedom classically, they are transferred to the quantum channel. So that's something maybe, this example is maybe more interesting to show what these correlations mean. And let's suppose that we have, for example, a pair of photons that share and possibly entangled state rho 0. There is a result that is mentioned here in this reference, that if you perform the channel, if you apply the channel to one of the qubits, and this system evolves then to a state rho, then the entanglement here quantified by the concurrence of the final state is at most the entanglement of the Choi matrix, which is this rho E. There is a typo here, it should be rho E. And which means in our case that if you have an entangled state to begin with of two photons and you upconvert one of the photons, then you can only get an entangled state in the upconversion to the extent of which that the dry field is non-separable. So there is some sort of transfer from the non-separability of the classical domain to the entanglement in the quantum domain. And that's something we wanted to observe experimentally. So that's what we did, and I'm going to detail briefly the experimental setup. So we start with a source, an SPDC source, to generate photons entangled in the polarization degree of freedom. We use a non-collinear Sagnac source, and we prepare the dry field using a combination of a quarter wave plate and a vortex wave plate. So we generate a field whose concurrence is given by this expression. So we rotate this quarter wave plate, and as we do it, we change the degree of non-separability between the degrees of freedom of the dry field. And then we use this dry field to upconvert one of the photons in a spin orbit QFC module, and the upconverted photon goes then through a spatial mode tomography system, while the photon that did not go through the spin orbit frequency conversion is measured directly in the polarization degree of freedom. So the photons are initially generated in 15-16 nanometers, so in the telecom range, while the frequency converted field is at 520 nanometers, as the dry field is at 780 nanometers. So we transfer the quantum information from the polarization degree of freedom of a telecom photon to the spatial mode of a visible photon. And this is a snapshot of what the quantum frequency conversion module is. It's basically another Sagnac loop followed by a polarizer to erase the distinguishability between the two loop directions. I will not enter into much detail on this. There is this reference for those interested, which is enough maybe to understand this scheme. So now to the results. So first, we wanted to see if we can actually transfer an entangled state that is initially an entangled state of two qubits in the polarization degree of freedom, and we upconvert one, so we end up with an entangled state of the polarization of a photon in the telecom range with the spatial mode of another photon in the visible domain. So that's what we did, and for that we used a dry field that is maximally non-separable. And that is characterized by a Choi matrix, which equals the identity, in which case the initial quantum state, and this is the experimentally retrieved initial density matrix in the polarization domain. And the quantum frequency converted state, in this case, is shown below. So here you can see in the labels that in the figure at the bottom, the second qubit here is encoded in the spatial domain. And we got good metrics for the frequency conversion, so there is a fidelity above 97% between the two states, which shows that our theory seems to make sense. But to verify this further, we also checked a direct violation of Bell's inequality just to ensure that we have an entangled state, and that's what we got. So basically, we verified that we have entanglement. And further on, we tried to show this bound that the classical inseparability imposes to the transfer of entanglement. And to do that, what we did was we changed this quarter wave plate angle, therefore changing the non-separability of the dry field, and we measured sequentially, we performed quantum state tomography of the upconverted state to assemble this figure that we are showing here. So basically it shows, in the blue squares, it shows the concurrence measured of the two-color hybrid state. And this continuous black line here shows the concurrence of the dry field. So it shows, with good agreement, that the concurrence of the dry field is imposing a bound to the transfer of quantum entanglement. Especially when we try to make a separable field here with a wave plate at 45 degrees, of course, because of experimental imperfections, we cannot completely kill the concurrence, but we obtain a maximum Bell value that is below what is necessary to show the non-locality. So there is seemingly a breaking of the non-locality at least. So this is just to wrap it up. And this is an example of a maximally non-separable or the maximally entangled state that we obtained with the two colors. And in the top row and in the bottom row, what you see is the more separable state that we got, which has a concurrence in around 0.2 or something. So just to wrap it up, just a comment before that, there was maybe a slide missing, is that, of course, we did the experiment for the spin and orbit degrees of freedom, but nothing prevents us to apply the same theory to 2 other degrees of freedom. For example, what is particularly interesting is the space and time. So if you have a signal in time, which is normally very difficult to measure, like a superposition of different temporal modes, you can use the temporal mode selectivity of the frequency conversion to up-convert it using a non-separable state of these 2 degrees of freedom. So basically, you transfer the quantum information from the temporal degree of freedom to the spatial degree of freedom, which we know how to measure very well. So that can be an option how to apply this new experiment to something that is actually useful for quantum information processing, for example. So just to wrap it up, we have shown then like a first demonstration of a transfer of quantum entanglement in quantum frequency conversion, especially from the spin-orbit transfer. And we showed more, that's the take-home message from this talk maybe, that the non-separability here is the key. So the non-separability of the drive field, which is a classical quantity, seems to be, in this rare example here, a necessary, although not sufficient, condition for the transfer of entanglement. And that's something we want to investigate further. So I would just thank you all, and also thank the collaborators of this work, which are André Jr. did the experiment with me, and Zela from Brazil, and Robert, that was my supervisor in the postdoc. So thank you very much.
So do we have questions on this side? I think we can move on to your side. Maybe there will something show up here. Dario?
Okay. Do we? We have one.
Thank you, Rafael. Very nice talk. So does this transfer occurs no matter what's the difference in the frequency domain?
Yeah. I mean, what limits
in terms of like the theory at least?
In terms of theory, it doesn't matter.
So if it was actually the same frequency, does you still like convert the information from the spatial to the...
Yes, that's actually what we did. We tried to do first, but of course we had problems with noise, because when you have the same frequency, we try to do it non-collinearly, for example, but it doesn't matter what angle and how you try to distinguish the modes, there is always more noise than signal. But in theory, nothing prevents you from doing it. No. Yeah.
More questions? Okay, if not, we can move to the next speaker.
Okay.
Aí pode deixar aqui, né? O pointer é esse aqui? Esse? Como funciona?
Essa bolinha aqui em cima é que dá zoom.
E o que não dá zoom? Como faz? E sem dar zoom, como faz?
Isso. Você só aperta a bolinha.
Sem dar zoom é aqui?
É, agora mexe.
Ah, essa é com zoom e o sem dar zoom é a de baixo?
Não, aí sem dar zoom a gente não tem, só se usar esse. É porque quando o pessoal tá digital, ele só vê se você fizer...
Mas ele estava fazendo um negocinho e ficava escuro e... Aí, isso, assim melhor. Tá bom, obrigada. É o mesmo botão?
Só tem que mexer.
Ah, tá bom. Beleza.
Okay.
So, yeah.
Ready to start? We have Patricia Castillo from USP São Carlos, and she's going to talk about a two-dimensional Bose gas to study quantum hydrodynamic instabilities. Patricia.
Yes. So thank you, everyone. Thank you, the organization committee here in São Paulo, and also Gustavo there in the US. So I will change a little bit the subject, I would say, I don't know. But I'm not going to talk about a device, a technological device, but I'm going to talk about a very flexible platform which can be used to study many, many different kind of phenomena, and in particular to be used as a quantum simulation platform, which I will just comment on. It's not exactly the topic of this talk here. Okay, so to pass, yes. So, and also I'm not going to give you any new results from my lab because we are actually building up a new experiment. So we started building up this ultra-cold atom experiment in the beginning of last year, and this requires some time to build up. Here I show some images of how this lab has been evolved during the past year. But I want to discuss how we can use ultra-cold 2D gases to study quantum hydrodynamic instabilities, which is also a very interesting topic. So first, let me discuss what are hydrodynamic instabilities. So these are instabilities that appear in fluids, and they are characterized by the exponential growth of a periodic and well-defined pattern. And they are interesting because they are phenomena that are present in our daily life, with some examples shown here. They have also relevant applications in industry, such as extraction of oil from the underground and the fabrication of nanomaterials, for example, with spheres. And they also appear in more exotic scenarios as solar eruptions and the atmosphere of gaseous planets, as we can see many, many of these instabilities appearing here in Jupiter. They have also a huge impact on modeling the Earth's atmosphere and climate, and they are one of the mechanisms behind the onset of turbulence in fluids. Okay, so then after this motivation, we can ask ourselves, how can we predict the onset and the evolution of such instabilities? So to model what happens with a fluid that will develop an instability, we need to know how the velocity field of this fluid evolves. And then we can use hydrodynamic equations such as the Navier-Stokes and Bernoulli equations. And if you want to completely describe the evolution of the fluid, we will have many degrees of freedom. So when we are dealing with classical fluids, what we do is we can neglect the fluid viscosity, which can be okay still if we want to look for the long-time evolution of this system. And we often assume that the velocity field will be rotational. This can be okay at the very beginning when we are looking for the onset, but after the hydrodynamic instability have developed itself, it's no longer true. We will have a very chaotic motion of this velocity field. So we can ask ourselves if there are any other type of fluid in which both of these conditions are true, and yes, there are superfluids for which both conditions are true. So examples of superfluids are liquid helium, which is strongly interacting, and then we will have to deal with the strong correlation between particles, or we can go for ultra-cold atomic gases, which are weakly interacting systems and can be easily modeled in terms of hydrodynamic equations. Okay, so what are ultra-cold atomic gases? So ultra-cold atomic gases are weakly interacting systems that are cooled to some tens of nanokelvins, and they will have some important features. First of them, they are macroscopic quantum objects exhibiting superfluid behavior, which means that they are irrotational fluids, and the most important signature of this irrotationality is the nucleation of quantized vortices, which plays a very important role in many dynamical studies in these systems. Another key feature is that these systems have a very high degree of control of its properties, so we can control atomic species, atomic interaction, the atomic statistics, temperature, number of atoms, trapping potential, system dimensionality, etc. And we have different detection techniques which allow us to extract many information about these systems. For example, density and momentum distributions. We can have single atom resolution while doing images of these systems. And we can look for coherent properties with interference methods. Okay, with all of these, I hope I have convinced you that they are very flexible and we can explore a vast range of physical phenomena, and in particular, emulate the physics of other more complex systems in an attempt to use them as a quantum simulator platform. But here, what I want to talk about is about hydrodynamic instabilities. And some of them have been already observed in such systems. For example, I showed 2 examples here. One, oops, I have to go back, sorry. One about a modulation instability after an interaction quench of a Bose 1D superfluid. And another one, which is a Kelvin-Helmholtz instability in a ring geometry. Okay, but what I want to do in my lab, I want to focus on 2 of the most common hydrodynamic instabilities, so the Rayleigh-Taylor and the Kelvin-Helmholtz instabilities. And I already showed a picture of them to you at the very beginning. So in the first one, we have the onset of Rayleigh-Taylor instability on this volcano eruption. And here, in these wave-like shapes in clouds, we have Kelvin-Helmholtz instability, and both of them can be modeled with a simple model that I will just introduce to you. So let's introduce a classical simple model for them, and let's suppose we have 2 fluids here, with the denser fluid on top of a lighter fluid and a less dense fluid, and they are both under the action of the gravitational force, and they can have relative velocity, which one with respect to the other, U1 and U2. And we are going to look how a modulation develops at the interface with a characteristic wavelength lambda 0. And for that, we will consider that these 2 fluids are irrotational fluids, and we can define an equation for the interface of the fluids given by a Fourier ansatz. So if we write down the Bernoulli equation in such a case and do some algebra, we can reach a dispersion relation that has this shape. And if you take a look on the Fourier ansatz we propose for the interface, we will see that if omega is positive and imaginary, this will characterize a modulation at the interface that will grow exponentially. And with time, the largest value of omega will eventually dominate the dynamics, and then we will have a well-defined pattern with a characteristic wavelength lambda 0 appearing. Okay, if we want to see, for example, Rayleigh-Taylor instability, how does it occur? It occurs when the fluids are at rest. So we can neglect these 2 terms here, the first one and the second one, and we end up with a simpler dispersion relation that has this shape. And we can calculate the maximum value for omega and find the characteristic wavelength lambda 0 here. And it has been shown that for quantum fluids, which I'm not going to go into the detail of the calculation because it's longer, but it's all derived on this reference here, we can find a similar equation which relates the superfluid properties of the system for this characteristic wavelength lambda 0. And how does it look like? So, for example, if I have a cup with water and I put a denser liquid on top, this denser liquid will start to go down into the water in these mushroom-like structures that are, in principle, spaced by this lambda 0 here. But if we have a 3D systems, what we do when we image is that we integrate along the direction of the image. So it's very hard to see the spacing between the structures. So it's much nicer if we go to a planar geometry, to a 2D fluid. Okay, so in the lab, what I want to do is really to look for this Rayleigh-Taylor instability in a 2D ultra-cold gas. And at the same reference I showed you before, that is written here, there is a theoretical proposal for doing that in a planar Bose gas. And they see the appearance of the modulation, and later on, they see the appearance of these mushroom-like structures in both components. So we have one component on the bottom, another component on the top, and they are pushed against each other by a constant force that can be optical, magnetic, you can choose. Okay, so to do that, I will work with potassium atoms, and I will choose 2 different hyperfine states of potassium. And potassium 39 is a nice atomic species because I can tune atomic interaction easily with Feshbach resonances. And I will use light forces to push the components one against each other. And the idea is to map all phases of this instability as a function of the atomic interaction to see where our results deviate from that simple equation that I showed before. Okay, so nice. So then I want to discuss very briefly how we produce these 2D gases. So in order to produce these 2D gases, we have to start with a 3D Bose-Einstein condensate, which I'm showing here in this picture here. So here is the vacuum chamber where the sample is produced, and this sphere is my 3D Bose-Einstein condensate. And then we have to compress this condensate to make it a pancake. So we do this with an optical lattice, and we will choose to do with an optical lattice that I can tune the angle between the optical beams that interfere in the atomic region, such that I can change the width of this pancake I produce. And then we need to add an in-plane potential that is going to be made by, it's going to be an optical potential made by reflecting a laser beam with a DMD, which is a digital micromirror device composed of many micromirrors which can be controlled independent to be on off, shining or not light into the atoms. And then if we do that, and we take an image of our cloud, we will see that the cloud will have the shape we imprint into the DMD. So it will be a pancake-like atomic cloud, very cold, with arbitrary shape that we can model by just changing the image we put here. And this gives us a lot of flexibility of what we can do with these 2D atomic clouds. So we can do different shapes, different uniform shapes. We can do non-uniform clouds as well. We can do lattice, etc. And this is something we are going to try in the future. And just very fast, just to finish with my time, I would like just to give you an idea of how is the status of this experiment right now. So here is again another picture of the lab in May last year and February this year, like just last week. And we see that this is, the experimental setup is now full of optics around and coils and everything. So it's really a building up experiment that we built over 2.5 years. And this is a scheme of the setup. So we have a big part here that is just used as source of atoms. We have an oven. We heat potassium up to 100 degrees. And then we do the first stages of laser cooling in order to transfer the atoms to this other glass cell here where the physics really happen. So right now we have the initial stages of this experiment really working out. So here we have our source of atoms that is a 2D magneto-optical trap that cool the atoms from the oven. And here in the center you can see a light red line, which are the atoms here. And in the science chamber, in the glass cell I showed before, we have a 3D magneto-optical trap, very shiny, very big, very beautiful. And later on, once we got this, so we have to do some steps of laser cooling to cool the atoms up to 6 microkelvin in order to transfer them to a conservative trap, which is made by 2 crossed beams in green and blue, here in this image, that crossed in the center of the cell. And this is where we are going to get the 3D Bose-Einstein condensate, which I said it's the starting point to produce the 2D gas. So today we are like that. So this is an image of the atoms in the dipole trap. So we have about 2 10⁶ atoms at 10 microkelvin. And here in the center is where they cross, this red circle here in the center. So we are very happy with a very good starting point to go for the Bose-Einstein condensate. And I would like to thank you all for the attention. Here we have the QR code for our website, and you can also follow us on Instagram if you want. And thank you very much.
Is there any question on this side? Yiwen.
Thanks for the really nice talk. I was just wondering, maybe I missed this, but how do you create the 2 different hyperfine species in the different parts of your trap?
Yes, so there are 2 possibilities that we will try to go for. One is just do a microwave transfer to different magnetic states and apply a magnetic field such that they will split. And also what we can try to do is to use this DMD, this digital micromirror device, to do a selective, spatially selective Raman transfer in order to transfer just half of my 2D cloud to a different hyperfine state. Yeah?
Yeah. Patricia, I have a quick question before I transfer over to you guys. Is it possible to look into, in the context of quantum simulations, right? You pose several challenges in understanding this hydrodynamic instabilities. So could you explore your system to set it up as a quantum simulator for answering open questions in the field of either classical or quantum physics?
Yeah, so there is always the motivation to use these systems to gain a further knowledge of classical systems, which have a much more complex velocity field. And but how much we can really do the link with this dynamical behavior, it's not completely, it's not completely true that we can really link the 2 of them very easily. We can, yes, I think quantum simulation in this case for dynamical properties is not super nice, but with optical lattices, this for sure we can use it, and we can, in principle, do it in the future if we plan to do something like a potential something like that. So we can play with optical lattices and study the dynamics of the system in the context of condensed matter models, this for sure. But with dynamical properties, we always motivate that we can gain further knowledge about the classical systems, but this is not completely true. We have to be careful about that.
Okay, thanks. That's it on our side.
Okay, so we are running out of time, so let's postpone the questions after the presentation, and let's go with the last presentation.
assim? Aqui fica assim mesmo? É. Tá.
Okay. Our last speaker for today is
Esse aqui.
Guilherme Temporão from PUC in Rio, and he's going to talk about tackling engineering challenges in metropolitan quantum networks. Guilherme, please.
So good afternoon, everyone. Today I'm going to talk about the engineering challenges in metropolitan quantum networks. So when I talk about quantum networks, I'm actually referring to a specific kind of quantum network for the most part of my talk, which are quantum key distribution networks. So the objective here is to create randomness across a network between two nodes in a secret way. So throughout history, we had some very well-known examples of QKD networks, such as the DARPA network in the beginning of the 2000s, followed by the CCOC network in Vienna, the Tokyo network, the Swiss Quantum Network. Many of these initiatives were QKD networks that worked as test beds for many manufacturers of QKD equipment, such that they could test their equipment and see how they could communicate with each other and so on. So nowadays, we have many initiatives, especially in Europe, for quantum networks. Maybe, but maybe the most well-known one is the Chinese quantum network, because it spans thousands of kilometers, both in optical fibers and free space through satellites. And we are doing something similar in Brazil. We have a project on building a quantum network, which is currently ongoing, which is the Rio Quantum Network, which aims to create a metropolitan quantum network connecting 5 institutions. So you can see here, this network connects the Federal University of Rio de Janeiro, the Pontifical Catholic University of Rio de Janeiro, the Brazilian Center for Physics Research, the Military Institute of Engineering, and the Federal Fluminense University. So these 4 institutions here on Rio side are connected through optical fibers. So there is an optical fiber ring connecting all of them except for the Military Institute of Engineering here, but we have a smaller segment of fiber. But this is a kind of backbone of optical fibers that was built decades ago with the purpose of research. So it's not, they're not fibers with commercial purposes. There's no data being transmitted there. So these fibers that were lent to us are actually dark fibers. There's no signal whatsoever going through them, which is very nice for us. And actually, we have 2 of them. So each side of this triangle here corresponds to a pair of fibers. Okay, and for this connection with Niterói, with the Federal Fluminense University, we don't have any dark fibers going there, but fortunately, there's a line of sight link between the roof of the CBPF building and the physics building here in the UFF, so we are implementing a free space link here of about 7 kilometers. So I'm going to talk about the main challenges that we are experiencing, and not only in our network, but as a general rule for QKD networks. So of course, we're going to talk about losses. Sometimes it's very hard to overcome the loss limits, but some clever arrangements can be done. I will provide you with an example. We have polarization fluctuations and phase drifts, especially in optical fiber links. So depending on the protocol, depending on the degree of freedom of the photons, where the quantum information is encoded, we have to take care of these effects. We have the problem of clock synchronization, which is critical for very high rate communication, where you need a timing jitter of maybe tens of picoseconds. And maybe the most critical one, which is noise from classical channels. So the coexistence, the same fibers of classical data and quantum data. Of course, there are more examples, especially in free space connections. If I have time, I can talk a little bit about them. So I'm here going to focus on one kind of implementation of a QKD link, which is called the Twin Field Measurement Device Independent Protocol, which, in my opinion, has a very nice balance, a very nice compromise between security and complexity, because it includes in the security proof this MDI protocols, measurement device independent protocols. They include in their security proofs attacks to the detectors. And the detectors are the most vulnerable part of any practical implementation of QKD. So in this example here, in this protocol, it's kind of meaningless to perform an attack on these detectors here at Charlie. So in this setup, we have the two parties that want to share a secret key, Alice and Bob. Instead of transmitting directly from one another a quantum state, they transmit quantum states to an intermediate station, Charlie. And here in this example, they prepare coherent states, and the quantum information is encoded here in these phases, phi A and phi B. And here in Charlie kind of makes something equivalent to a Bell state measurement. So depending on the outcome of this measurement here and on the choices that were made by these random number generators here, Alice and Bob, one can infer what was the choice of the other, and they can distill a secret key after some post-processing. And this twin field variation has a very nice feature that is related to the losses. As you can see here, for example, if we assume symmetrical links with the same transmission in the channels, we can show that the probability of having a detection event here at Charlie scales with T. However, the total transmission between Alice and Bob is the product of the transmissions, right? So the total transmission between Alice and Bob would be T squared. So in this protocol, we are more robust to losses than in standard MDI QKD, because the key generation rate scales with the square root of the transmission between Alice and Bob. So this is a way of kind of getting rid of the high losses, which are really limiting for QKD. And this way we can overcome this so-called PLOB bound and go above what was proposed before. So this is what we have chosen to our implementation. The problem is we have to distribute a phase reference, right? Because these two phases here have to be kept stable over time. So we have to kind of create some kind of interferometer or somehow distribute a phase reference. And because of this issue, we have chosen to apply this idea that was published in 2022, which employs a SINAC configuration. Because as you know, in a SINAC interferometer, if you have phase fluctuations, this cancel out for the clockwise and counterclockwise pulses that propagate here. So in the same way, the quantum information here is encoded in this relative phase between these pulses. So the relative phase between the clockwise and the counterclockwise pulse. So as we have this ring, right, in Rio, so it's I think it's a natural idea to employ this configuration, because we have this automatic phase stabilization. But we have some challenges in this configuration, this SINAC configuration. The first one is polarization, because the phase is kind of automatically compensated, but it's not true for polarization, because whereas the clockwise pulse sees a unitary transformation U, the counterclockwise one will see U dagger. And in general, these unitaries are not self-adjoint, so these matrices are not the same. So you need some kind of polarization tracking, such that you can have maximum interference here back in this beam splitter. So the two polarization states but arrive at the same to have maximum visibility. So we have to employ some kind of polarization control, but these polarization control schemes are very well known. It's not a problem. You just have to take care and implement them. But there's a different problem here that's not present in in some other kinds of twin field QKD, which is the problem of Rayleigh backscattering. Because as you can see here, the encoding is performed here at Alice and Bob, but the pulses come from Charlie. The laser pulses come from Charlie. But when they go out of Charlie's offices, here they carry no information whatsoever. So there's no meaning to attenuate them here. They can go classically to Alice and Bob, and then they attenuate the pulses to the single photon level, and they encode the quantum information. But when you do this, when you send bright pulses here, you have the problem of Rayleigh backscattering. So these Rayleigh backscattered photons here, they generate noise. They increase the noise floor, so you decrease the signal-to-noise ratio. So you have to take care of that. One way is following the idea of this paper here, which is on archive. You work on bursts. So you send a burst of data, and then you wait until the Rayleigh backscattering falls to a low level, and then you send again, and so on. And they have made the calculations, and they show that the optimum duty cycle for this burst is around 33%. So you lose around 2/3 of what you could because of Rayleigh backscattering. So now we are currently working with this link here between PUC Rio and CBPF. And it doesn't look like a sine arc, right? It's just a straight line. But remember when I told you that we have two fibers. So we still have a sine arc. We have one fiber going one way, another fiber coming back. So we still have a loop, but the two fibers are bundled together in the same optical fiber cable. So there's still a sine arc configuration. Maybe it's clear to see here in this picture. This is our loop, and we are now working on this issue of synchronization, polarization control, and we solve the two problems at the same time using this auxiliary wavelength here. So I have a classical channel which is multiplexed with the quantum channel, and use this classical channel for both polarization tracking and for synchronization. This is just a previous result without the polarization control, such that you can see that there's a decrease on the interferometric visibility here. We don't go all the way down here because of polarization fluctuations. So this is exactly the reason why we need polarization control. So we're using this side channel. We pulse it in order to get this clock for synchronization. This is a way of implementing synchronization without resorting to external systems such as GPS or White Rabbit or any other commercial solutions. So in here, we don't have the problem of Rayleigh backscattering because Alice and Charlie are together, so we already send the pulses in a single photon level. We don't have this problem of Rayleigh backscattering. Now, finally, we have to deal with this problem of integration with classical networks, and this is a hard problem to solve. This is the count rate in a DWDM channel at around 1550 nanometers when you use a tunable light source, a tunable laser going from this wavelength here to this one, and we monitor the noise counts in the fixed wavelength around 1550. And as you can see, you have a lot of noise, and the reason for this is spontaneous Raman scattering. And this becomes even worse when we have multiple channels, which is the reality of any populated fiber, right? You have many multiplexed channels in different wavelengths, and all these effects add up and you have a lot of noise. So this is really hard to overcome. We have shown this paper here from 10 years ago that the effects can be really dramatic. It can really decrease the length of the quantum link. So this is very hard to overcome, the spontaneous Raman scattering, because you cannot filter it. The scattered photons, they fall exactly in your quantum channel, and they have the exact same wavelength as the photons in the quantum channel. So one way to overcome that is to use this idea. Maybe you have seen this paper in the end of last year by the group of Prem Kumar. It was on the news in many websites. It was the first demonstration of quantum teleportation in a populated fiber. I mean, in a real network with classical data. And if you pay attention here to their experimental setup, they use the 1300 nanometer portion of the spectrum. So they move away from the 1550 nanometers, which is the most used in telecommunications because of the lower losses, right? The minimum value of the loss in an optical fiber is around 1550 nanometers with an attenuation coefficient of 0.2 dB per kilometer. So they move to the second telecommunications window in 1300 nanometers, where the attenuation coefficient is almost the double. It's 0.35 dB per kilometer, just to get rid of this noise from Raman scattering. So this is the solution that they have achieved. So they moved to the so-called O-band. The O-band is exactly this region of the spectrum, around 1300. And they show that you can have many milliwatts of power, of classical power, and the visibility here of their Hongo-Mundell interference here in Charlie is kept in a very nice level. Unfortunately, I don't have time to talk about the free space link between the UFF and CBPF, but the main challenges here are, of course, filtering. You need to do a lot of filtering in spatial modes, spectral mode, and temporal modes. And, of course, you have to take care of turbulence effects, especially because in our link, we are over water, so we have a lot of evaporation. So we have a lot of turbulence because of that. We cannot neglect the effects of turbulence. So just to wrap up, so in QKD networks, we have this compromise between security and complexity. In this case, I have showed a protocol that is somewhat simple. It does not employ entanglement. It's kind of simple to implement as long as you take care of this phase tracking problems. Losses can be mitigated. This is an example where we can scale with the square root of the transmission coefficient, but of course they remain a fundamental limitation in all QKD protocols because losses impact directly the secret key generation rates, which are usually low for long distance links. They are in the order of kilobits per second for long distance links. So it's very, very hard to increase this number. So for optical fiber networks, we have many solutions for polarization, fluctuations, phase fluctuations, clock synchronization, but there's no known way to get rid of this spontaneous Raman scattering noise. So the coexistence with classical signals is really hard. So one possibility is the one that the group of Prem-Kumar has done. In others, is to move altogether to the O-band at the cost of increasing the losses. Because if you are in the 1300 nanometers, your loss coefficient is much, much higher. When we have, especially in the case of the quantum real network, where we have this hybrid scheme of optical fibers and free space communication, we need active filtering and schemes for mitigating turbulence, especially because we have to couple the light into a single mode fiber. And so it's really important to take care of that. And I didn't have time to talk about this reconfigurability, but we employ switches for decreasing the size of the Sagnac loop whenever needed, so we reduce the losses. But we have to take care of polarization, so we need to employ active polarization tracking, and we have to employ this limited duty cycle for the bursts to get rid of the Rayleigh backscattering. But in a final remark, the challenges go beyond the physical layer. I'm just talking today about the physical layer, but when you think about a network, it has many abstractions layer up to the application layer, like in classical networks, and of course the challenges go to every other layer. So thank you for your attention. This is the team of the Rio Quantum Network, and these are the guys that do the hard work, the students. So thank you very much for your attention.
We have a question here. Again, making a short one. So are you considering moving away from 1550 in this, or you can count on having your fibers kept dark for you while you do your...
Yeah, in the real quantum network, we can stay at 1550 because we have dark fibers. But this is a very unusual situation. It's something that is really rare in the real world. So for us, it's okay. It's fine. We can stay at 1550. But for many other networks in the world, maybe the solution will be moving to the 1300 nanometer window.
That's it on our side.
Are there quick questions on this side? Okay, if not, we can thanks all the speakers of these sessions. Yeah, let's do the group photo here.
Oh, we had a group photo before. Now
okay, so
like
we can probably, yeah, okay, so we can probably conclude the connections, right?
Okay. Okay, see you all.
Okay,
Thank you.
yeah, thanks a lot.